What is going on, everyone? This is Sean from All Things EV, and I couldn't be more excited about this video because it's been one that I've been wanting to do. I in my research of batteries and battery cells, this has been a very common topic for my channel over the last several weeks. I came across a very knowledgeable, incredible human being, Ravi Kempaiah, and he is a PhD scholar at the University of Illinois Chicago, where he is focusing on advanced battery materials for his PhD thesis. His background is material science and nanotechnology. He got his Master's of Science in Chemistry and Nanotechnology from the University of Waterloo in Canada, and his second Master's of Science from the University of Maryland College Park in Materials Chemistry. Ravi is a big proponent of EV, sustainable transport, and the current Guinness World Record holder for the longest journey on an electric bicycle. Ravi, thank you so much for taking some time to drop some serious knowledge about batteries. Welcome.
Sean, thank you so much. I really appreciate it. I have followed your channel for quite some time. I'm excited to be on this podcast. You always put out really good content, well-researched, and I think that's what drew me into your channel. And I'm happy to contribute to that, what your endeavor, where you're really good, putting out good content, and we're sharing the right. You're sharing your passion. You're sharing a lot of good information. So I'm very excited to be part of this.
Yeah, it was very flattering when I reached out to you by email and you said that you've watched my videos. Creating content online is just a very interesting thing because you don't know who's watching, and people can know a lot about you, but you know a little bit about very little about the people on the other side. So I over the last several weeks we've been in touch. We've talked about how we might be able to present battery technology in a way that is going to be helpful, informative, and, as you said before we hit record, allow people to have a greater appreciation for the intense research and technology that helps electric vehicles power forward. So I think with that said, I'm going to kick it over to you, and I'd love for you to just sort of start off by how in the world you got interested in batteries and battery technology, because you've spent a great deal of time learning about it at universities, and you'll soon sort of transition on from university into some very exciting things that maybe we can get to at the very end. But how did you gain an interest in batteries?
Great, sure. That's a very good question. My journey started in 2013. So I had been in the industry before. Even before that, I lived like a monk, and then I was in the industry. Then I thought, well, the industry 9-to-5 job is not really exciting for me. So I wanted to get into research. And in 2013, I thought, man, there must be a better way to transport somebody from point A to point B than a 4,000-pound metallic box like a car. So I researched what I could use instead of a car when I was in Maryland, and I came across something like electric bikes. And I thought, wow, this is interesting. Then I dug deeper into that, and then I bought an electric bike. Even then, my interest in electric vehicles or battery was not high. But in 2016, I did something interesting. Let me share some slides with you so we can walk through the whole journey together.
Yeah, and while you're doing that, I'll just sort of add in here that it's been impressive to learn about your expertise. I mean, even just when you sent me the bio about your educational background, it is a true testament to your commitment to learn about batteries and battery chemistries and so on. So I think that people who are watching this are really, really going to appreciate the technical specifics that we'll cover today, and we'll try to at some points here take a pause. If I mean, for me, I think my brain will just be incredibly full by the time we get to the end. But we'll stop at different points and just sort of break it down to a very simplistic level, so that for those that don't understand or have an interest in chemistry and science, that you're still following along in grasping how this technology powers vehicles like the Tesla. So with that said, I think you're probably ready here. I'll go ahead and pass it over to you.
Well, thank you, Sean. Thank you. That is very kind of you to say. As I said, my journey really took a turning point in 2016 when, with the help of some really great people, my friend Lenny Mattioli and other people from a company called Stromer, which makes high-end electric bikes. I took a journey from Madison, Wisconsin, and crisscrossed the nation all the way to San Diego. So this journey was about 5,100 miles, and it took me 32 days of riding, total 34 days. And finally, I was able to get a approval from the Guinness World Records that it is indeed one of the longest journeys on an electric bike. So when I got home and I did the math, actually this is a picture of a Tesla and then my electric bike that I used. This was near Big Sur, or one of the Pacific 101 routes. So I came back and then I did all the math, and then what really astounded me was how much little energy I used for the entire 5,100 cross-country trip. So to do 5,100 miles, the cost came out to be close to $5. Even in the worst case scenario, if some states have maybe 20 cents per kilowatt hour, even if you use that, it still comes out to be close to $7. So for $7, you could go 5,100 miles, and that is incredible. So I thought, wow, that's amazing. And then, I realized that electric bicycles are incredibly efficient. They only use 10 to 20 watt hour per mile for a reasonable 170-pound rider. If you compare that with Tesla Model S, that uses 275 to 350 watt hour per mile. And electric bicycles offer a whole bunch of other benefits, like health benefits, parking, and all that stuff. So I thought, wow, this is really the future, because I thought if something clicked in me that, okay, this is something that I should spend my life on, because this is truly going to take over the transportation. So in 2016, I started researching batteries, and that's how I got into this. One of the questions I keep wondering is, why did lithium-ion batteries become the default option for electric vehicles? Why not some other kind of batteries? To understand that, we have to take a step back. And if we see this here slide, what we are seeing here is in 2003, we had phones and laptops and EVs that looked like this. We had Nokia phones, and EV1 was like this. And the phone here, didn't have Wi-Fi, didn't have GPS, did not have 16 megapixel camera, did not have a whole bunch of other things. Whereas in 2013, just 10 years from now, then you see really incredible progress. You have phones with octa-core processors. You have phones, laptops that rival desktop batteries, and then you have cars that are incredibly powerful, fast, and efficient. So how did we get there? There are two kinds of revolution that really made this happen. One is the electronic revolution, where it's called Moore's law, where the size of a transistor goes down by half every 16 to 18 months. So now that's why we were able to go from a transistor size of 150 nanometers to 10 nanometers, even 5 nanometers in the recent years. And that was the electronic industry revolution. And at the same time, there was a revolution in lithium-ion industry. And at this point, we really must appreciate what Tesla did. They took some big risks when nobody used 18650s back in 2005-6. People like J.B. Straubel, Mark Tarpenning, and the other co-founder, they really thought, okay, We are going to string together thousands of laptop batteries, and then we are going to build a roadster. They put all their might, energy, money, time, everything to get 18650s into mainstream. And then, of course, laptops took over. So right now we're here. It's a huge progress in a span of 10 to 15 years. So one of the reasons is the energy density that is offered by lithium-ion batteries. What I mean by that is, there's a term that is specific energy density. How much energy can you store per kilogram of material, battery material? So the conventional lead acid batteries offer anywhere from 30 to 45 to 50 watt hour per kilogram. So if you replace, let's say, Tesla Model S battery, entire battery pack with a lead acid battery of similar weight, you would be able to go anywhere from 45 to 60 miles. Okay. Now, if you replace the entire Tesla Model S battery pack with the nickel metal hydride, which is used in Prius, Camry hybrid, Highlander hybrid, Avalon, and some of these cars, you can probably go anywhere from 85 to 110 miles. All right. For the same weight, if you have the lithium-ion battery, you can go 250 miles. Such a big jump, almost 100% jump, and that really revolutionized because it is light compared to lead acid or nickel metal hydride. At the same time, packs a lot of energy. So this was one of the key drivers for making laptops. If you take the screen of iPhone or Android Galaxy S10, it's a huge screen with the quad HD, almost 1600 pixels, and such high number of pixels consume a lot of power. And then you have 8 core processors, you have camera, you have GPS, you have Bluetooth. Where does the energy come from for all those processors, right? That comes from the lithium-ion battery. And that is the real revolution. Without the lithium-ion battery, electronic industry wouldn't survive. So, and Tesla played a huge role because they were the first ones to take the risk. So I'm really admire JB Straubel and Tesla team for what they did.
Yeah, I think it's really remarkable. Elon Musk gets a lot of the credit for the growth and the technology of Tesla, but JB Straubel is a fundamental part of why Tesla has gotten to where they are and why the auto industry is following along. He is not he's not a front man. He's actually very impressive when he's on stage with a microphone. He's pretty well spoken, but it seems like he prefers to be behind the scenes. But he's doing a ton behind the scenes. Wouldn't you agree?
I agree. I know he was the mastermind behind the supercharger network. He was the mastermind behind the Gigafactory. Of course, there was a whole team, but supercharger, he led the whole product development and execution and all of it. And without the supercharger, Tesla wouldn't be where they are today. The supercharger network played a huge role in making things so much easier for people to make a decision. To really get a comprehensive understanding of how these lithium-ion batteries are done, we really have to go back to the basics. This is a slide from one of the presentation given by Kurt Kelty. Kurt Kelty was a phenomenal man. He was one of the key pillars who led the development of Gigafactory and the marriage between Panasonic and Tesla. So he made this presentation, and they actually have really deep ties to mining industry, the metal processing industry, metallurgical industry, the logistics between all of those teams. So they have a phenomenal connection there, and they actually confirm and secure the supply for many years in advance. So to lock in the price, because the prices of some of these raw materials are vulnerable to market situations. So they work very closely there. So starting from the mining, what we see here, the raw materials, nickel, cobalt, aluminum, iron. Iron is not used in the Tesla batteries, but nickel and cobalt and aluminum are used. From there, the smelting and refining happens, and then they prepare the precursors for NCA, which is the chemistry used in Tesla Model S. But what are those precursors? They are nickel sulfate, cobalt sulfate, sodium hydroxide, and from the mines of Chile or Bolivia or some other places around the world, they get secure lithium, which comes out as lithium carbonate, and then from that they get lithium hydroxide. So lithium hydroxide on the one side, nickel, cobalt, and sodium and aluminum on the other side. You get all this precursor. They go through a whole bunch of metallurgical processes, refining, smelting, purification, and then finally, you combine them in the right kind of proportion to get NCA, which gives you if you mix them in the wrong proportion, you lose the capacity. So it's done in the right proportion, right process conditions, and finally you get NCA, which ends up in your NCA battery. So the whole cycle life, takes many, many months. And even if you were to have the mines right next to the gigafactory, do all these things, it'll still be a month worth of work, and it takes, it's a lot of work. So that is just for the NCA, which is the cathode. Similarly, the anode part, which is the graphite, you have to have a graphite mine, and then the petroleum refinery supplies you with the additives and pitch black and conductive additives. So you get natural graphite from the mines, and then it goes into this process where they combine the additives and binders. Finally, you carbonize them, and then there's something called graphitization at very high temperatures. And then finally, milling is a process where they break down, it breaks down the big chunks into small pieces. And then finally, you blend them, and then finally, you get the graphite anode. This is a really bird's overview of the whole process, because there are so many details into this, so much energy, effort, work that goes into this. But this gives you an idea of how much work it takes just to get the anode and the cathode, right?
I've got a question for you about one of the pieces there. Top left, when it says that there's the refinery involved in the oil, the petroleum, that's to process those pieces of the thing, or can you explain that a little bit more?
Sure. So gasoline production involves a lot of byproducts that is used in our hair products, in oil, lotions, plastic, so many other components. So that is all the byproduct of petroleum refining. So gasoline is one, and then kerosene, jet fuel, and a whole bunch of other byproducts come out. And pitch black, and then coke. So these are all coke, and they're all part of byproducts of the petroleum refining, and they're used in small quantities. Basically, you want to bind the particles of graphite in a proper way and shape them, because that's the product. So they use refining pitch black and additives to bind the small products, small graphite particles together. But they're not the majority here. Graphite is still the majority, but we do have to use small amounts of binders and additives from the petroleum industry.
Got it. So the binders are made are a petroleum byproduct to bind the graphite.
That is correct.
Understood. Okay, thank you. Carry on.
All right. So now we have an idea where the graphite and the NCA, which is the cathode and the anode, come from. So we always want more range. We always want higher cycle life. You want your batteries to last 15, 20 years. You want your car to go 500 miles. But this is a problem that every battery scientist faces on a day-to-day basis. And this has been the conundrum for the last 30 years. And, this is something we work on every day. This is the challenge. The challenge is, if you try to push the energy density, that means you want 400 mile, 500 mile range battery. That's great. Okay, you can do that. Then you want to minimize the cost. You can do that. Then the cycle life takes a hit. All right, if you increase the cycle life, and then if you increase the energy density, then the battery cost will be something like $100,000 just for the battery. To get all three high in the desirable range, it's extremely difficult. I mean, I can't tell you how difficult it is. And the whole effort of the battery research community goes into this, to get high energy density, to get low cost, to get high cycle life. This is, if the whole battery problem can be condensed into one slide, this is it. You want to get all three high, but it's pretty difficult. Next, the current state of the art. Right now, we are at a stage where you have 250 watt hour per kilogram for the battery configuration. So a simple cell would have current collectors, cathode, separator, anode, and the current collectors. We will show a detailed picture later in the later slides, but this is the current state of the art. So to increase the energy density, right, how do we do that? Well, if you use a material like NCM 811 cathode, which is NCM means nickel, cobalt, manganese in the ratio of 8:1:1, and a artificial or a composite graphite high quality, then you may be able to get 255 watt per kilogram. That is equivalent to what you see in the current Tesla Model 3 or Model S. Now, if you want to go even further, let's say you have a Tesla Semi coming up and you want to have a lot of range for the Semi, then people are working on how to do that. And so there are different approaches to do that, but there are many, many challenges. One approach is you replace the graphite anode that we saw on the previous slide, graphite, you replace that with the pure lithium anode. If you use pure lithium metal, there's a problem called dendritic formation. Dendrites, they're like sharp teeth. They grow out of these structures and then they poke through the cell and then they short circuit it, basically making the whole cell defunct. So that's a problem, and that's a big problem, and people are working on using lithium anode. If they can succeed, we will see about 410 watt per kilogram. That means a recent Tesla Model S with this kind of battery would be able to go, instead of 360, probably 470 miles. But it's still a long way. And the ultimate would be to have conversion cathode and then lithium anode. These are something like lithium sulfur conversion cathodes. If you can do that, you get 495 watt per kilogram, then you're looking at 500 plus miles. But it's still very, it's still a long way to go. These are all challenges, but these are some approaches that scientists are taking to increase the energy density at the cell level.
What would you guess is the likelihood that the industry will eventually get to that 500 watt hours per kilogram? Is it just a matter of time and research and money, or is there a big chance that the industry won't get there? What does that look like? How difficult is it to get to that higher energy density?
So I have a slide to explain that. Hold on a second. All right, I'll come to that slide. But to get to this point from here, what we are right now, we are at 255. To get to 495 watt per kilogram, it's an extremely hard scientific problem. It's that involves thousands of PhD students. Their whole PhD life will be dedicated on the thousands of them. And it is, I think, at least 10 to 15 years ahead. And that's still a speculation because it's an extremely hard scientific problem. But you can expect at least 300 watt per kilogram in the next few years. Right now we are 255. I would say by 2023, we are looking at 2022, we can look at 300 watt per kilogram. That's possible because people are working on silicon composite anodes. There's a company called Maxwell Technologies, Innovate, and many other companies. They have silicon dominant anode. So if you use that kind of anode and a smart, highly capable cathode, you're able to push from 255 to 300, and that's possible. So that will render your Model S with 400 and something plus 450 miles range. That's pretty decent. So another way to increase energy density is increase the voltage, operating voltage. Right now, a standard Tesla Model S cell has an operating voltage between 3 to 4.2 volts. The lower end being 3, the upper end being 4.2 volts. Now, if you push the 4.2 to 4.5 using different kinds of cathodes and anodes, then you're increasing the energy density. Basically, within the same volume of cells, you're able to eke out a lot more energy. But it comes with its own limitation. What are the limitations of using 4.5 volt battery from 4.2? Well, The electrolytes then will have to be designed for such high voltage. Right now, the current kind of electrolytes that we are using will break down at such high voltage, and then we will have more parasitic reaction. We will talk more in detail about the parasitic reaction, how that happens. But basically at 4.5 volts, you will have a lot of parasitic reactions. What it means is your cycle life will go down. Instead of your 8-year battery warranty, you may get, instead of 2000 cycles, you may get only 1500 or 2000 cycles. That you don't want. So that's the challenge we have to address if you use 4.5 volts to get high energy density. But these are some of the ways people are approaching to increase the energy density.
So increasing the voltage means that there's higher amounts of electricity going into the batteries to, let's say, charge it.
That's right, because a higher amount of electricity means you're pushing in more. Because let's say by magically we changed all your Tesla Model S cells from the NCA to some of these higher capacity cells which are operated at 4.5 volts, then instead of a 100 kilowatt hour pack, overnight your pack has 120 kilowatt hour. So because the operating range has increased from 4.2 to 4.5, so to charge 120 kilowatt hour pack, obviously you need more electricity. So you will be pumping more electricity to that. But 4.5 volt means basically the force with which electrons can go through. For example, think of it as like this. You have a water tank, okay? You increase the height of the water tank. What happens to the speed with which water comes out at the bottom? If you increase the height of the water tank, then the velocity goes faster at the bottom. Similarly, if you increase the upper end of the voltage, then it means electrons are much more eager to go to the other end, which is the cathode. So we are talking about anode, cathode. So I want to take a step back and give you an idea of what we are talking about, what it means, what we mean by anode, cathode, separator, all this. So this is the Tesla Model S floor structure, and you have the battery there, and battery has 16 modules, or close to 7,100 cells, all right? So 18650 cells. And if you take those modules apart, you will end up with 18650 cell like this. Now, if you open that, you have something like a jelly roll here, which comprises of separator, anode, and cathode, and electrolyte. So basically, even though the name says lithium ion, if you start opening things up, slowly you realize that the battery is comprised of many other materials, not just lithium. So you will see, if you magnify this structure here, the jelly roll, this is what we see. This is like atomic scale, microscopic scale, or nanoscopic, not atomic, but I would say microscopic scale. So at that scale, we have graphite as the anode, and the cathode, lithium cobalt oxide. This is the chemistry that is used in iPhones, lithium cobalt oxide. If you replace the cobalt oxide with nickel cobalt aluminum oxide, then you have the Tesla Model S. Basically, if you keep changing the cathode, we keep moving from one chemistry to other. So if you change cobalt oxide, then from cobalt oxide to NCA, then we are switching from iPhone chemistry to Model S chemistry. If you change this to manganese oxide, then we are switching from Model S chemistry to Nissan Leaf chemistry. If you change that to nickel, cobalt, manganese oxide, all the changes that happen on this side, the graphite remains the same, anode remains the same for all these chemistries. What changes from iPhone to Model S to Nissan Leaf to Chevy Volt is this side, cathode. Cathode is what changes. And there is a separator between them because you want to keep them apart. You don't want to short circuit your battery. So from every Nissan Leaf to Model S to iPhone to other, BYD has a chemistry called lithium iron phosphate. That's again on this side. And lithium only constitutes 2% of the cell. But because they are the main ions that shuttle back and forth between these 2 points, we call them lithium ion cell. But in reality, we should call them nickel aluminum cell. But
I've got a question. I've heard a lot of people say that are the batteries in phones the same as the batteries in vehicles? Because I think that the lifespan of batteries in, let's say, a smartphone aren't as long as like an automotive grade battery. So can you maybe dive into a little bit of the different how those are different phone versus an automobile that has a quote unquote lithium ion battery?
Sure, sure. Well, it is true. The Apple iPhone has a prismatic cell or a pouch cell design, and whereas the automotive Tesla Model S has an 18650, and the electrolytes they use, the structure that we see on the right top here, it sits in electrolyte bath. The electrolyte will be different, the additives used will be different, the operating, the BMS, the battery management system will be different. So in phones, what people mostly care about is lightweight, and then you can afford to change your phone battery every 1 year, 2 years, because it may cost you like $50 to $100. But you can't afford to change your car battery every 2 years or 1 year. So people have taken tremendous precautions to make sure it lasts 10 years, more than 8 years, and I think the Tesla comes with 8-year battery warranty. That's because they limit the operating voltage. They have a very sophisticated BMS. They have very complex additives that go into the electrolyte to minimize any parasitic reactions. And the form factor itself is different. The iPhone uses a flat pouch cell kind of design, a prismatic pouch cell, whereas the Tesla uses a 18650 cell. So, and then, we have thousands of them. In a car, we have thousands of them, whereas in the phone, it is just one piece. There are no 10 or 5 small components coming together. It is just one cell. So those are the changes. But essentially, phone also has graphite anode and the lithium cobalt oxide cathode. But as I said, the electrolyte, the additives, the way the BMS is structured, and just the volume and the scale is completely different.
I also had another question about the voltage piece. So the Porsche Taycan, which will come out later this year, has a charge rate of 350 kilowatts.
Right.
That's up from what the Model 3 can do at 250 kilowatts and what the Model S and X can do now at 200 kilowatts. So does that play into, do you think that they've increased the voltage of their batteries to allow that, or what is that a factor of, that vehicle can charge at 350 kilowatts, and does that have an impact on the lifespan of those batteries that will be in those vehicles?
Sure, there will be some differences and implications of fast charging. 300 kilowatt is extremely high rate of charging. Basically, what it means is you're taking all the lithium on the right side here and then pushing them back to this side anode. So you're taking all that stuff and pushing them here. So the graphite itself will have to be a very sophisticated, it's not a natural graphite, it's artificial and combination of artificial graphite. There are specific ways these things are manufactured and combined. As we talked about, graphite has its own additives and binders. So the kind of binder chemistry, the kind of additives that you use for anode has to be optimized to accept lithium at really fast rate. And then you have to optimize the cathode to let go of a lithium at really fast rate. And you have to optimize the electrolyte bath. And then if you keep pumping them, the battery gets really hot at that kind of fast charge. So you have to cool it down. You must have very sophisticated liquid cooling. So all of that will be, I'm not sure, to be honest, I have not driven the Porsche Taycan, and I don't know the real details about it, but for sure there will be differences. And one of the reasons Tesla has been a leader is because they were one of the first ones to implement glycol cooling. So we will get to the effect of heating and high temperature and high voltage, how negatively it affects the batteries, and how Nissan had to go through some problems. We will get to that later, but I'm sure the engineers at Porsche has done their homework. But I'm very curious to know what kind of chemistry they have changed, optimized. to use 300 kilowatt hour because that's pretty high. So I don't want to speculate and give misinformation, but for sure there will be big differences. Differences. I don't know how big it is, but there will be differences. Also, I want to clarify some of the misconception people have. People think in an 18650 cell, lithium ions go from one end to the other end, and the electricity or the lithium the current travels this direction, which is not true. The current doesn't flow from one end to the other. So if you open up the 18650 cell, you have sheets of cathode, anode, and separator. And in the microscopic scale, this is how it looks like. So the distance they have to travel is between this jelly roll. This is micron scale. So they just have to travel micron scale. They don't go from one end of the battery to the other end. They just travel, and there are layers and layers of these. So they travel back and forth between those layers. So I guess we have given our viewers an idea of what a lithium ion battery, how it functions, at least an overview. So you have anode on one side and the cathode on one side and the separator. Now, where is the bottleneck for energy density? You know, everybody wants higher, longer range, lighter batteries, long-lasting batteries, but there is a bottleneck, right? There has to be. Otherwise, you know, that's a challenge right now, which is the energy density. So the energy density problem can be traced to one material more specifically. So on one side, the graphite anode that has a 360 milliamp hour per gram capacity, energy density, okay? And the cathode, for example, the Powerwall uses lithium NCM, lithium, nickel, cobalt, manganese. That has a layered chemistry, and the spinel oxides are used in Nissan Leaf. The BYD buses and trucks uses lithium iron phosphate. So all of that we are talking about on this side. And this side is the bottleneck. This side is the problem. Positive electrode, the cathode is the problem. The problem is they have lower energy density than graphite, between 160 to 240, 230 on the higher end. As they say, the strength of a chain is in its weakest link. So the energy density of a cell is dictated by the energy density of the cathode, which is the positive electrode. Graphite is able to store much more lithium, but the cathode is unable to hold that much lithium. So unless we increase the energy density of cathodes, we may not be able to push beyond. You know, we can't expect like really super long range vehicles unless we have improvements in the positive electrode side. So how do we do that? So there are ways to, so we talked about increasing the energy density, right? By increasing the voltage, we can do that. By changing the anode configuration, by changing the cathode configuration. And there is one specific chemistry that has been, I know people are researching very widely. That is the NCM chemistry. NCM chemistry was invented by two people. It can be attributed to two very respected researchers, one at Argonne National Lab, Professor Michael Thackeray, and the other one from Dalhousie University, which is Professor Jeff Dawn, who is also a pioneering scientist and who heads the Tesla's research plan. They have an exclusive contract. So they were some of the pioneering scientists for NCM chemistry. What we are seeing here is a phase diagram and how people are trying to optimize the NCM chemistry. It is just one chemistry, right, that is used in the Powerwall. So people can appreciate, you know, how much effort people are, you know, scientists across the world are putting into this. So initially, this whole NCM chemistry started from, you know, these stoichiometries. 1, 1, 1. What does it mean? Nickel, cobalt, and manganese in the ratio of 1:1:1. So that means 0.33 nickel, 0.33 cobalt, 0.33 manganese. Or 5:3, half of nickel, 0.2 cobalt, 0.3 manganese, or 4:4, stuff, you know, of this sort. And they had energy densities of 150 to 160 to 155. As you see, you know, this is less than the cathode, which is 360. Sorry, anode. Anode already has 360, and the cathode is the lesser, the weaker point. So they had 155, 164, 155 amp hour per kilogram or milliamp hour per gram. Now people have optimized the chemistry to to go with lesser cobalt and increase the energy density. So the high nickel cells, which are called NCM 622 or 811, uses high nickel, so 6 nickel to 6 is to 2 is to 2. So that has 178, which is a pretty good improvement, and 811 has even higher capacity, 185. So 8 nickel to 1 nickel. Sorry, let me repeat it. 8 nickel, 1 cobalt, 1 manganese. So there, as you can see, we are decreasing the content of cobalt, and cobalt is actually one of the costliest cathode materials. And 90 to 80% of the cobalt reserves in the world comes from a small place in Africa called Democratic Republic of Congo. It's a small country, very corrupt politicians, very inhuman working conditions. So people are trying to get away from cobalt. So as you can see, people are already moving away from cobalt. We have 622, 811.
Is it expensive because it's coming from one region and they have the monopoly on it?
Not just that, cobalt itself is a byproduct of nickel mining. There's no straightaway mining of cobalt. It is a byproduct of nickel mining, and then it is if there is no big demand, if the demand for nickel surges in a country like China, they're constructing some other stuff. So if they want to use for some other purposes, nickel prices vary, and then the cobalt prices are fluctuating a lot. So a lot of other factors. Of course, the labor cost is one, and then they control. If one country controls the whole supply chain, then it's up to their whims and fancies how they want to regulate it. And of course, the companies like Tesla and others have a deep ties into that mining industries, but still, mining of cobalt itself is a very labor intensive, very equipment intensive, cost intensive process. So the labor part, the demand from the other industries, and the political situations of the country itself dictate the price of cobalt.
Do
Right
you know
now,
much about who? I had read in an article recently that China is buying up a lot of these mining companies in other countries. Does China control a lot of this, or I guess where my head is at sort of long term is if Tesla wanted to have control of making sure that raw materials were being sourced in a fair, friendly, environmental way, is it possible that they could get into the game of buying companies that are mining the raw materials?
you're absolutely right. If we go back to the slide that Kurt Kelty had, yeah, this one. So in the slide, in the presentation, he also mentioned that they have deep ties to these mining industries, mining companies, and they actually invest into them. So to scale up, they themselves cannot scale up because the demand for EVs is growing so high. So companies like Tesla, Gigafactory, Panasonic, they invest into these mining companies to scale up. And Kurt also mentioned, that they're establishing sustainable practices. They ensure the companies have certificates of origin and many other quality controls in check. So to make sure it's done in the right way. But it's hard to micromanage at that level, and it's really hard. I'm not in that industry, but Gigafactory and Tesla really do have deep ties into this. And China, as for your question, China is indeed purchasing a lot of the mining companies because their own local market is really expanding rapidly. So they are purchasing it. So China is being a major player. They can dictate the price, but to what extent, I'm not in that industry, so I really can't comment very accurately. One of the questions that Tesla has been working on is cobalt really needed? What we see on in this picture is a mine in Congo, and there are some really heartbreaking pictures on the internet. You can check, but basically cobalt comes from mines like this, and the cobalt oxide or the cathode structure looks like this. you have layers of oxygen, cobalt, oxygen, and then there's a layer of lithium. So the lithium goes in here, there's an oxygen on this end, in the middle you have cobalt, then you have oxygen on the other end, then cobalt. It goes on like this. So people really want to get away from cobalt because of all the reasons we mentioned, geopolitical reasons, the cost. The cost right now is, I think, $27,000 per ton or something like that, per ton or metric ton. But it's really high compared to all the cathode materials. Cobalt is the highest cost. Aluminum is really cheap. Nickel is also cheap, but cobalt is really high. So people do want to get away from this. And a lot of research has been going on in this field. And recently, there was a really interesting article by Professor Jeff Dahn. Their group did a very systematic study into different alternative chemistries, and they wondered if they can really replace cobalt. And the summary of this research is cobalt is really not needed. They thought cobalt is needed because the initial understanding of the battery community was that if you take away all the cobalt from the middle of these structures, scaffolding, right, the structure will collapse and you may compromise the power density of the battery. So they were able to compensate for the cobalt using aluminum. So that's how the NCA came into existence. They were able to compromise the power density by bringing in aluminum and nickel to a certain extent. And NCA is a chemistry that's still not very deeply known. Professor Dahn's group is working very extensively on this. But the community thought if you take away the cobalt from these structures, I think we showed some of these structures already. So we have layered structure cathodes, we have tunnel structures, you have spinel. So they have all the structures. They act as a kind of a scaffold where lithium ions can go and reside. So if you take away the cobalt, the consensus among the scientists was that it will compromise the structural integrity and the cycle life. But the recent study shows that you can push the nickel content really high. For example, what you see is the testing of a battery that has 100% nickel oxide and lithium nickel oxide as the cathode. And then they have 95% nickel, 5% aluminum, 95% nickel, 5% manganese, 95% nickel, 5% magnesium, and finally 95% nickel, 5% cobalt. And they concluded that cobalt plays a very minor role and you can neglect the role of it. And so, the people are engineering chemistries without cobalt and it is okay. And you can still get pretty good cycle life and energy density.
The cost. So, I mean, that seems like a very positive direction that the industry is heading to remove cobalt for various reasons. One of the probably important ones is cost. The other important one is this social geopolitical impact as well. So I guess that seems good, but are we just sort of shifting the issue or the conflict from cobalt to nickel? I mean, so if companies end up using more nickel, does that create another issue of demand, which increases the price of nickel, as well as could that social impact also just shift from cobalt over to nickel as well?
Well, the nickel reserves are much more than cobalt reserves. So the nickel prices are still way down. I think it is in the range of $1,600 per ton or in that ballpark, or a little bit more. But it is still orders of magnitude less expensive than cobalt. So because we have a lot of reserves all around the world for nickel, not just in Congo, then it sort of balances out, normalizes the problem. You're not really dependent on one small region of the world to get all your cobalt reserves. And we do have enough nickel to supply for the rising EV demands. Did I answer is that?
Yeah, I think so. Yeah, I mean, it sounds like because the materials are more readily available across the globe, that it should help keep costs down. And of course, anytime you have a centralized place for materials and someone who wants to exploit that and people, then that becomes a problem. But it sounds like because nickel in its raw state is much more available around the globe, that should help keep costs down and prevent it from being a sad social injustice.
That's right. That's right. So as you can see, if you have 95% nickel, only 5% cobalt, or even, if you can completely replace cobalt with aluminum or manganese and still get very 90, 95, 98% of the original energy density, then you really don't need cobalt. As of now, Tesla already uses very less cobalt in their Model 3. So going away from it, it's not too far. I mean, they can go cobalt free fairly soon, but they may still have cobalt until this kind of chemistry goes into production. But they already have less than 5% cobalt, so less than 10% cobalt. So they're less vulnerable to the changes in cobalt industry as compared to other, for example, Apple is a lot more vulnerable because they use lithium cobalt oxide as the cathode. And of course, for using one Model S battery, you can have thousands of iPhones. So the scaling is different, but still you get the idea that, people are able to move away from cobalt. So the other question is why do car makers use different kinds of cell setups? What we see here in this is a picture schematic that shows cylindrical cell. This is a prismatic cell, and this is a pouch cell. Cylindrical cells are used by companies like Tesla, whereas the pouch cells are used by companies like Chevy. GM uses in the Chevy Bolt and Bolt. This is a series of pouch cells. They are stacked one on top of each other to get the right kind of capacity. So there are pros and cons to each, and but the needle favors the needle moves in favor of cylindrical cell because the cost per kilowatt hour per cylindrical cell is still way favorable than pouch or prismatic cells. You can also see pouch cells in some of these electronic equipments, phones and other places. But I'm sure, there are still some car makers like Nissan Leaf, Chevy Volt, even some, Volkswagen or Audi could be using pouch cell design. But Tesla is still ahead of the game because they were able to engineer the pack, the BMS, the cooling, the chemistry, and of course the cost. The reason why, there are three reasons. There are three reasons why cylindrical cells are still favored. One is cost. Cost per kilowatt hour is still cheaper. The second is the metallic jacket that you have around the 18650 gives some structural rigidity, and then it can be used as a scaffolding. So the material, the floor of the Model S can still take the load and give it certain kind of integrity that pouch cells are unable to. Pouch cells are big compared to the cylindrical cells. They have a flat surface that doesn't provide you with any kind of structural support. And there is another reason why cylindrical cells are favored. That is, you have 7,000 plus cells in a Tesla Model S, all right? And if you want to use your Tesla Model S in ludicrous mode, you want to go 0 to 60 in 2.8 seconds, 2.9 seconds, then you're flooring the pedal, and there's something called battery warm up, and so the battery is getting ready for that kind of usage. But in such high power draw situations, the load is distributed over 7,000 cells, whereas if you floor the gas pedal on, or the accelerator on the Volt, it is distributed over a few hundred pouch cells, maybe 300, 400. Whereas in the Tesla, it is distributed over 7,000 cells. So as a result, that yields to certain longevity of the battery. You're not stressing the cells too much, and you can supercharge your Tesla, even though Tesla recommends not supercharging your car every day, but let's say if someone were to only supercharge the car, it is still less than 1C or close to 1C. Less than 1C is not going to degrade your chemistry. But if you're going to, supercharge a Chevy Volt or some other chemistry, then, for example, you mentioned Porsche at 300 kilowatt hour. I mean, I'm not sure what kind of liquid cooling they have. If they don't have a sophisticated liquid cooling, then such high power draw could degrade the chemistry faster. So that's why Tesla is still using the cylindrical cells, but there are other configurations available, and they are bigger in size, and they're not, they're cost, ineffective compared to cylindrical cells.
This was quite surprising to me that you're saying that the cylindrical cells are less expensive to produce, because every company right now, every automaker that has a pending EV coming out is using the pouch style cells, with the exception of Rivian. Rivian is the only one that I know of at the moment that is going with the 18650 cylindrical cells, which I believe they're getting them from LG Chem.
Right.
So if those cylindrical cells are less expensive, why are companies, do you think, using the pouch style cells?
To be honest, I don't know the reason why they picked LG Chem. I know many other companies use it, but GM, if you look at it recently, I think Monroe Associates in Detroit did a teardown of Model S and BMW i3 and one other car. They found that the Chevy Bolt is basically, they took the Spark or some other platform, and then they put, instead of the engine, they put the motor, they put, they didn't have to build it from the ground up, whereas the Model 3 is built from the ground up. So they may have a contract with LG Chem because they have, they supplied the batteries for Chevy Volt before, previous to the Bolt. So there could be a multitude of reasons, but from all my analysis, and cylindrical cells is a very established way of making the industry has been dialed down so nicely that the cost has come down significantly. Maybe the cost is pretty close to 18650. It may not be lesser than 18650, but maybe it is pretty close. Maybe because they have a contract. To be honest, I don't know, but all the research suggests that 18650 still have an upper hand when it comes to price.
Yeah.
Otherwise, Tesla wouldn't use it.
Yeah, I think it's really fascinating. I mean, to me, it appears like the cylindrical cells have better redundancy. So if one cylindrical cell goes bad, it doesn't impact the entire pack or the modules. So you're ensuring the safety and longevity of the battery pack with the cylindrical cells. The other thing that it appears like is you can draw power from cylindrical cells better than the pouch style cells, as well as manage the temperature of the pack through cylindrical cells far better than pouch style.
That is correct. Imagine one cell or maybe 5 cells, individual cells, go bad in a pack of 7,000. That's still not, less than 1%, less than 0.5%. But if you have 300 pouches and then 5 of them go bad, it's already more than 2% or 1% defect. So that could render a whole module malfunction, and render them ineffective in a pack. So maybe they have an engineering solution for that, but it is wise to distribute it over a larger number of cells. And as I said, it also gives structural integrity because of the metallic jacket. It gives you certain strength to the floor. So that's one of the reasons. And more importantly, you can customize the shape. The pouch cells are big. They take a certain, if you look at the Chevy Volt, there is a big hump running from the front and to the back of the car because the pouch cells take up that space. And I think there is a reason why Chevy Volt doesn't have a 5-seater. It's only a 4-seater because the shape of the battery takes up so much space that they couldn't put the 5th seat. Whereas the small dimensions of 18650, makes it easier to shape it in any way you want it. This is an interesting slide that mentions, I didn't want to predict it because I'm not an established expert in the field, but the Professor E. Choi from Stanford is a very well-respected researcher, and he put out this graph, and I thought it is very appropriate to share it here. So from his presentation, it looks like he thinks the current state of the art is 250 watt-hour per kilogram using graphite anode, NMC cathode. And there are companies like Maxwell Technologies, Innovate, that are using silicon dominant anode, where you're pushing the, basically you need a smaller or a thinner anode for the same NMC chemistry that you have. So as a result, in a given volume, you can pack more energy. That's how you get 400 watt per kilogram. That could come about in a few years, 4 or 5 years. But we can safely say that we will see 300 watt per kilogram in the next 3 years. In moving on, in further ahead, 5 to 8 years from now, lithium metal, if the scientists solve the problem of dendrites, then you can see lithium metal with NMC that could give you 500 watt per kilogram. Basically, the Tesla Model S could go 600 miles with a similar battery pack without doubling the size of the battery. If you can get lithium metal and NMC, it could go 500 miles plus. That's really exciting, but it has lots of challenges. It is a very hard scientific problem. Ultimately, this is like 10 years down the line. If you can get lithium metal and sulfur conversion cathode working, then you're looking at a Model S with a 300 kilowatt pack. But that's just pure speculation. It's an extremely hard scientific problem. But as I said, safely we can say 300 watt per kilogram is definitely doable. So how do we get 18650s? That's another important piece of information, right? It's good to know how 18650s come about, and there's so much work that goes behind making a single cell of 18650. In the previous slide we talked about mining, and Kurt Kelty mentioned about refining, hydrometallurgical processes, pyrometallurgical processes, and from there, you get the refined powder. That powder is the starting points for 18650. The graphite powder, the NCA powder, you get the powder in really high quality. They are very high quality powders, right? And then you mix them in the right chemistry, stoichiometry, with the binder, with the additives, conductive additives, and then you disperse it. And this is where the Tesla's acquisition of Maxwell Technologies could play an important role. These two steps. First one, slurry making, and then the coating and drying. In the first step, you use the powders, cathode and anode, and then make a slurry out of it using a solvent. It's a laborious process. It is a labor-intensive process. It is a equipment-intensive process. And then you make the slurry, you coat it on a current collector. Like, for anode, you put it on copper. For cathode, you put it on aluminum. Then you have large rolls. These rolls run for miles. And then you have to dry it. You coat it and dry it. Okay? These two steps are very labor-intensive. And then there's something called calendering. Once you calendering is basically compaction of the electrode material on the current collector to get the highest energy density and the shortest conductive path for the lithiums to flow through. Basically, you want to make the lithium's pathway as simple and easy as possible, so they don't have to tackle a lot of obstacles in the cathode structure. And then once you do that, you have to make sure the cathode is of certain quality. So you characterize the cathode material and anode material to make sure there are no large pores, the compaction is right, and everything is okay. And then you cut it and punch it to the exact size you want for the 18650s. And then once you cut it, you assemble it into a jelly roll that we saw in the previous slides. You have a jelly roll in a cylindrical format, and then you add electrolyte into that in this stage. And then you have the formation. You initiate the cell for a certain voltage, and then you test it. Make sure it runs for, out of 100 cell, in a batch of 100 cells, you take few of them out, make sure it gives you the right voltage, right current, power density, energy density, and then you ship the whole batch. So this is the process flow chart. As you can see, it is a very labor intensive process. I'll give you a brief overview of the first two stages, right? The slurry preparation and the coating and drying. This is where the Maxwell technology could make a difference, because in slurry preparation, you need large quantities of solvent. You have to mix it. You need large equipments. It is time consuming, and time is money in an industry that has to churn out gigawatts of energy every year. If you remember, the gigafactory is right now limited by Panasonic's ability to produce. They wanted 35 gigawatts hour, but they're able to do only 25 gigawatt hour. So time is money in such situations. And if you have to do slurry preparation, coating and drying, the coating and drying itself takes like 18 hours, and 18 hours is a lot of money, right? If you can combine them into one process, you save a lot of steps, equipment cost, material cost, and then the time itself. And then it goes to calendaring. So the coating and drying and calendaring. So this is where the Maxwell's dry electrode technology could make a difference. And I'm sure that is one of the reasons Tesla acquired them. So after calendaring, cutting it, cell assembly, and then, it goes to the electrolyte filling and formation.
I've got a question. And there's obviously no way to know what's behind the curtain and what Tesla's plans are for Maxwell, but a few questions. So the first one that I'd love for you to just sort of provide your insight into is why, and this is a question that I've seen in comments of some of my previous videos. Why do you think that Tesla got Maxwell for so inexpensive, and why weren't if Maxwell has such a fantastic technology, why weren't more companies grappling to buy them?
I have also wondered the same. Why didn't Mercedes Daimler acquire it? Why didn't BMW take on the Maxwell? Well, they are still far behind in terms of the integration. When it comes to Tesla has Gigafactory lined up. They're vertically integrating themselves. They have the technology for batteries. They have the technology for manufacturing, and they have number of scaling is. I mean, who else is selling the number of cars that is equal to Tesla pure B electric vehicles? I mean, maybe Nissan Leaf, but they're not in the same segment, and they're not doing different models. They're doing just one Nissan Leaf.
What about battery producers? I mean, why wouldn't a Panasonic or an LG Chem have been interested in this? It totally makes sense as to why another automaker was not interested, because they're just not as far along with their own self-production of battery cells. But to me, it would seem like a no-brainer for a company like Panasonic to snatch them up.
I really don't know why they didn't, because this is well, Panasonic is also making prismatic cells for Toyota. Okay, Panasonic is also building different kinds of chemistries for Toyota. So they are also not putting all their eggs into one basket, and there is some. The relationship between Tesla and Panasonic is an interesting one. But Panasonic, as you said, right, they could have acquired it, and they did not. I don't know.
Yeah.
I don't have that insider information.
Yeah. Okay, so my next question, and again, there's no way to know what's going on behind the curtain here. What sort of obstacles would Tesla face if they decided to become their own battery cell producer? Because right now, as it stands, you have Tesla and Panasonic who have agreed to partner together to not only build the Gigafactory but also produce the battery cells.
Right.
If Tesla now has Maxwell, they have a relative understanding of how to produce a battery cell after acquiring Maxwell. Does Tesla really need Panasonic? Since they now have, of course, they've simplified the cell production process by using the dry battery electrode. So is it plausible again, I want to preface this. There's no inside knowledge here, but between either of us. But is it plausible that Tesla could cut out Panasonic and start producing their own battery cells, and therefore control a little bit more of that process, reduce cost, and so on?
My hunch, my feeling, intuitive feeling is that no, because Tesla, it's a symbiotic relationship. They license Panasonic is building stuff for them, and it's not, it's Gigafactory is a joint venture from Tesla and Panasonic, but it is Panasonic who brought in all the technology into the scaling, the refined process, industrial processes, small, details of optimizing each step. What you see in the slide here, each step has thousands of sub steps and optimizations, and it is Panasonic that brought in all that know-how. And I don't know if they would give it away, all of that to Tesla, or to have that kind of know-how into building that large scale would be pretty difficult for Tesla. So my hunch feeling is that Tesla simply can't kick out Panasonic, because Panasonic has, I'm sure they have protected themselves with certain NDAs or licensing and other agreements. Tesla may have opened their patents, but between Panasonic and Tesla, I don't know. And Tesla really, I don't think it was Tesla who brought in all this battery technology. It was Panasonic, the strength of and the might of Panasonic that made Gigafactory possible. And of course, the investment and the vision and the demand. Tesla created the demand. Panasonic brought in the know-how. They were able to marry these two together and build something beautiful like Gigafactory. But I know.
Yeah. I think it's a fair rebuttal. Your response is a fair rebuttal, and it could very likely be the situation. And one of the other potential scenarios is Tesla allows Panasonic to leverage Maxwell technology and integrate it into the process. So there is this sort of, mutual symbiosis. I guess one other case in support of Maxwell, they're not new to the game. They've been making supercapacitors for a very long time, and I'm sure there are some differences in production of supercapacitors versus lithium battery cells, but I think that Maxwell is bringing to the table some tenured knowledge of production of energy cells.
Absolutely, that's exactly the slide is. What you see in the slide is a coating and drying oven and a machine equipment. That you see the small rolls here going in. They are baked, and then you remove the solvent, and then the drying happens. It comes out on the other side. This is just a laboratory scale, lab scale, very small scale stuff. There would be rows and rows of such equipments in Gigafactory or wherever the 18650s are done. And if you're producing 25 gigawatts of 18650s, you need large quantities of equipments like this. And Maxwell's technology, they call it dry battery electrode, and they remove the drying process, which minimizes the time, and then coating, which involves solvent, you remove that. So then you're saving a lot of equipment cost, material cost, and time. So that's where the Maxwell really makes a difference. And calendaring is basically a process, but that anyway has to be done, whether it is Maxwell technology or wet chemistry, you have to do the calendaring. Basically what it does is, you see the rolls going in here, they come out after the baking, right? Then it goes to calendaring, wherein you see the particles here have some gaps between them, pores. You don't want those pores. You want the material to be as dense as possible, so you can pack a lot of energy in a given volume. So the rolls here, you pass that electrode material through these rolls, between these rolls, and it compacts the cathode and anode such that they're tighter bound. So the pores are eliminated, and the lithium can have connective pathway to go to the current collectors. So they don't have to struggle between these pores to get to the current collector. So calendaring is a process that anyway has to happen, but Maxwell Technologies will impact these two steps, coating and drying. So that's where the Maxwell plays into picture. And the dry battery electrode is basically, they mention that it is not electrostatic spray or other kinds of coating methods. They don't, it's a proprietary technology. They don't mention how they coat it. But what basically dry battery electrode is, we talked about how from mining you get powders, and then through hydrometallurgical processes you get refined powders. So basically you take those powders, add binder to bind them together, and additives to make it conductive. And then Maxwell uses a technology where they can take this powder and then to make into a calendar sheet, okay, that can be laminated onto a current collector. So basically it eliminates coating, which involves solvent, and then drying. So how they do it is, it's a proprietary technology that I don't know, but they're able to do this effectively, and they claim that the energy density of such a cathode is better or on par with the existing state of the art. So that's a great thing. If Tesla is able to utilize that technology to enhance the efficiency, then certainly there will be big changes. It will improve their efficiency.
When Tesla has talked about cost per kilowatt hour, they actually were doing this pretty frequently on earnings calls, that their goal was to get down to $100 per kilowatt hour at the cell level. And then all of a sudden, about a year ago, they stopped talking about that. And in fact, they got questions from analysts that were on the earnings call, and they sort of brushed off the questions about it. Do you think that this acquisition of Maxwell is the pathway to get them below the $100 per kilowatt hour at the cell level?
Well, breaking down the cost is one of the big challenges, but is Maxwell a tipping point for such, as an inflection point to go below $100? It could very well be, but at this point, do you happen to know what is their cost per kilowatt hour?
No, I mean they stopped talking about it about a year ago, and if I don't recall the specific amount, but I do remember about a year ago, when they started ramping up the production of the Model 3, it was somewhere around $115 per kilowatt hour or something like that. They said they were getting really, really close, and I think that they said that they would be at the $100 per kilowatt hour level by the end of last year, 2018. But they have never said anything since, and it was always a little bit of a mystery to me as to why they decided to stop talking about it. And that was sort of where my mind went, which is, if this Maxwell thing is as important and strategic as it appears to be, that dry electrode process should save Tesla a significant amount of money, which of course has an impact on that per kilowatt hour cost at the cell level.
Yeah, as far as I remember it was around $135 or $150 per kilowatt hour. And I didn't follow much after that. So the Maxwell itself may not be a huge cost saving, but because they're vertically integrating, they may see benefits better than many other manufacturers. But I don't want to, give misinformation. So I would say I really don't know if it tips the scale below $100 with the Maxwell. But for sure, it will aid the efficiency, because you're basically cutting down this kind of equipments, or maybe you don't need as many drying and ovens and coating machines. So that will save some money. And then if you're producing gigawatts of packs every year, and if you can smartly integrate the Maxwell stuff, and you can somehow increase, they also claim they were able to increase 16% more energy density compared to the existing wet chemistry. And that is a big deal. If you can increase energy density, that's a big deal. So it is not just the cost from the material standpoint, but also energy gain you get is dollars saved. So as long as you can eke out more energy density from the existing materials, it's a gain. So both materials and energy cost, you know, when this technology will go into production, I really don't know, but I'm also looking forward to reading more about it, and maybe we can do a separate video on that in a year's time.
Yeah, no, I think that would be a really, really great idea. And for those that are watching this, please put in the comments if you'd like to see a part 2 of this where we dive deep into it. We've been aware, and I think you've been following this as well, this tension between Panasonic and Tesla in terms of battery cell production. They've been at 25 gigawatt hours for almost a year now. Tesla wants to be at the 35 gigawatt hour level. Part of me wonders if this as well is a potential solution to increasing that production of the cells, because Maxwell says that it will reduce the amount of space that is required for producing these cells, and it will take less time to produce the battery cells with that DBE technology. So I really do wonder, and again, there's no way to know. It's just an interesting conversation to talk about the implications of Maxwell, but I wonder if they're thinking that Maxwell will help them get to that theoretical 35 gigawatt hour production level.
Right. Well, if you take out the drying time, the coating time, and somehow replace, instead of 30 hours, you're able to reduce it down to 15 hours. That's 15 hours worth of money right there. And the energy density, I'm also, I'm sure scientists are already testing the energy density of the cells with the DBE technology. If it is up by 5-10%, that's a big deal, right? And so, yeah, I know. Let's keep it. Let's keep our eyes open and see, if how that plays out, and that'll be interesting to observe. Right now, because there's not much data available right now, because it's not into production. I don't know if it is in production already. How many cathode chemistries have been tested using the DBE technology? All of these are unknown, so it's hard to make a educated guess at this time. But 6 months from now, we will have more data, and I'm pretty sure we could have a better insight into the process. Another thing we were discussing, in our emails, was the recycling, because we are producing huge number of lithium-ion batteries. Every company is getting into it. Mercedes, Toyota, GM, Tesla, Nissan. Where do these batteries go after 8 to 10 years? That's a big question. And if you don't take care of that, that will be irresponsible of us, because then we will affect the environment negatively. Instead of making it green, it will not be so green. It just so there's a huge push for recycling these batteries in a sustainable way, in a way that doesn't harm the environment. So what happens is you get the EVs, right? And this is from a scientific paper. I have linked it here. And you have the spent batteries here that come out after 8-10 years, or let's say you said you had a battery replaced.
Yes.
That battery goes for reconditioning and recycling. Tesla has their own program of reconditioning and recycling it. So they may not crush it and do it, but they may be different. So if 80% of the pack is good, only 10 or 20% of the pack is bad, then the recycling process will be different. But let's say your capacity the battery capacity has gone down by a significant amount, then the recycling may be a better process. So basically what happens, you take the battery and then you want to separate out all the constituent elements: iron, aluminum, copper, nickel, the plastic, the metallic jacket casing, the electrode material, NCM, and electrolyte material, that's organic toxic material. So you want to separate them out in a way that can be reused, right? So there's a lot of research going on. Some universities in Boston or Worcester actually got some grants to perform that kind of research. So this is how the recycling happens. You get the spent lithium-ion batteries, If it is significantly degraded, then you crush them such that all the parts, come apart. Then the plastic shells, the metallic jacket, and the cathode material, the current collectors, right? You get all that stuff, and then whatever the important stuff that you need, the cathode, the nickel, the cobalt, aluminum, and then some of those material will be subject to pre-treatments where they're screened, and then the ultrasonic washing separates out based on the density, based on the material, based on what can be reused or not. So once the outer jacket is taken off, then the inner part will be subject to the screening and washing. And then we end up with three kinds of materials grouped together. Plastics will go into one bin, the electrode materials, whether it is nickel, will go into the nickel bin, the cobalt will go into the cobalt bin. If it is completely amalgamated, it's pretty hard. Then the electrode materials will be, it's like a clump, cluster of these materials that will be together. And then the current collectors, aluminum, copper, current collectors will be in the other bin. Then they're subject to a very vigorous hydrometallurgical and pyrometallurgical. Hydro means you use very strong acids that can leach the material. Basically, use sulfuric acid, hydrochloric acid, trifluoroacetic acid, citric acid. You pick the kind of acid that will dissolve only the material you want. It won't affect the other materials. So you pick the kind of acid that is good for, let's say, aluminum or copper or cobalt or nickel. Then you leach that away, and then you have a slurry or an acid which contains dissolved nickel or cobalt, aluminum. And then you have pyrometallurgical processes where you can, it is further using heat. And once you have done that, then you have a container full of, let's say, acid that has cobalt in it. Then you subject it to chemical precipitation or electrochemical deposition, where you're able to extract some of those cathode in a reversible way. So once you extract those nickel or cobalt, then that may not be as good as the starting material of the battery. We saw in a slide where it came out of the mine, they refined it, and it was pure. So the cobalt coming out of this structure may not be as efficient or pure as the initial starting material, but that's an area of research that is happening, how to get really high quality cobalt and nickel and electrolytes or other materials from the recycling.
I think this is really insightful, because this is one of the things that detractors of electric vehicles say is a problem, which is, once the battery has run the course of its life in the vehicle, it just gets tossed in the landfill. But according to what you're sharing here, it's not true. It gets recycled and reused. So I guess the question is, once the materials are recycled and they're broken apart, where does that stuff go, and what, since it's not as pure as at the beginning of the battery's life, those materials, what can they be used for? Are there really easy use cases for recycled materials like that?
Sure. Nickel is used in the steel industry, right? And cobalt is used in other steel industry also, and it is also used for making magnets. Nickel is also used in making magnets. So nickel cobalt materials are also used in catalysis in the petroleum industry and many other industries. As a material scientist, I know nickel and cobalt have extensive usage in the metallic industry, especially steel industry, where you don't really care about ultra pure nickel or ultra pure cobalt. As long as it is above a certain threshold level, you're good, and it can be used in, for example, let's say construction industry. Construction industry, for that steel, you need some dopants to strengthen the steel. They use chromium, they use nickel. So in all those cases, this kind of materials can be used. It need not necessarily go back to the lithium-ion battery. It can be used for different applications. Basically, we are trying to minimize one usage case where you just use it for one per application and throw it out. Once it is done, it can be used for different applications. That's a better approach for recycling. So as of now, I don't think it is used for batteries right away, but there are tons of other applications in the chemical industry and metallurgy industry.
That's great. And I think recycling it is far better than it appears like. It's far better than using an internal combustion engine where the power that petroleum is burned up and comes out the exhaust and into the air that we breathe.
Right, absolutely. I'm sharing the link. The citation is here for the paper. It is all about the progresses in research in recycling of lithium-ion batteries after from EVs. So I'll share the link. The readers can look through this. There's so much research happening in this area as well. So it's an exciting time to be. And more importantly, do we still have the time to go over the effect of high temperature and high voltage?
Absolutely. This is a good one. And I will have a few more questions here too.
Well, if there's a wonderful, wonderful talk on YouTube by Professor Jeff Dawn. He goes into a lot more detail why lithium-ion batteries die. But the gist is that if you have to take just the takeaway from the whole talk is, if there are two things, that is, high temperature is bad for lithium-ion cells, and the time spent at high voltage is bad for lithium-ion cells. If you have a practice of charging your Tesla or any electric car to 100%, you may want to rethink it a little bit, because charging to 90% will enhance, significantly. I mean, if you get 2 years extra, 3 years extra out of the existing battery just by charging to 90%, why not? And maybe in some cases where you want to go, long road trips, maybe you can charge 100%. That's okay. But here is a graph, and this is the paper, Online State of Health Estimation on NMC Cells Based on Predictive Analytics. I'll also share the links for those scientific papers. So they did full equivalent cycles. If you charge and discharge 100% all the time, you'll reach 80% in less than 2,000 cycles. That is less than 80 years, 5 years maybe, right? And that's 100% depth of discharge. But if you do 80%, you're looking at a lot more cycles. If you do 60%, I mean, that's even better. So ideally, you want to charge to 70 to 80%, then you're looking at easily 8 years of life. That's why Tesla doesn't recommend using supercharger, because it is pumping in electrons at a very high rate. And also, if you discharge your battery 100% all the time and charge it up to 100% all the time, it leads to what we call parasitic reactions. And there's a slide that talks about what these parasitic reactions are. So the summary is, time spent at high voltage is bad. Let's say, that's why I know many Tesla owners set the timer such that just before their commute starts at morning 7:30 or 8 o'clock, their car reaches 100%. Just before that, not the night before, just before 8 o'clock, it reaches 100%. That's fine, because then it is not sitting at high voltage for a long time. But if you charge, that's why cell phones that are plugged in overnight, people have a habit of, when they go to sleep, they plug it in and they take it out only in the morning. Those kinds of cell phones only last a year or less, because sitting at 100% for long times is bad for the chemistry, both at the anode level and the cathode level. It degrades the chemistry and it leads to parasitic reactions. And high temperature accelerates these parasitic reactions. It just makes it difficult for the lithium ions to diffuse. And what we see in this graph is the effect of temperature. So the ideal temperature to operate is between 20 to 40 degrees Celsius. And this is for different charge rates, 1C, 2C, or 3C cycles. 1C means you're able to charge your Tesla in 1 hour, and you're able to fully discharge your Tesla in 1 hour. That's not the case. Most people don't discharge the Tesla battery pack in just 1 hour. It's much more than that. They drive for maybe 5-6 hours and then it goes down. So discharge is not 1C, but the supercharger is close to 1C, less than 1C, but still this graph is useful because it gives you the ideal operating temperature window. What happens if you use it above 40 degrees Celsius on this side or less than this? If, many people complain that in the winter time, the range for their electric car goes down. Why is that? Because of this. Let's go back to this slide. All right. And in this slide, we have the cell, and the whole thing is sitting in an electrolyte bath. The electrolyte is filling in all the annular spaces between these materials. Now, let's say it's winter in St. Paul, Minnesota, and it's maybe 10 below zero. What happens is the electrolyte freezes. Even though the glycol cooling in Tesla helps mitigate that, it'll still go down. It becomes thicker. It becomes thicker. So what happens is now the electrolyte becomes like a honey instead of water. So lithium ions, instead of swimming through like water like liquid, or less viscous liquid, now it has to flow through like a very viscous mass like honey. Now basically, it's harder for them to reach from this side, from the anode to the cathode. So when you're driving your car, the lithium ions are going from anode to the cathode. So they have to swim through a very viscous jelly-like material that's hard. That's why the range goes down. Now, that's why you want to preheat your battery in the wintertime so you don't lose. Then if you heat it, then it is not so viscous anymore. Then you can still get decent range. All right, now that's on the other side of temperature range. Right now, what is the effect of high temperature? Now we are looking at the right side here. This can be better explained with an example. In 2015, Nissan had to settle this lawsuit. The settlement was for the amount of, I think, $24 million. And this was for many, many Leaf owners who owned the 2001, 2012 Leaf. The lawsuit claimed that Nissan Leaf, even now, I still can't believe the engineers at Nissan don't have liquid cooling. It is still air cooled.
I agree.
It's insane. And the customers in Arizona, some parts of California and Nevada, they had so much degradation in the battery. They lost 3-4 bars in a few years. So they filed a lawsuit, and they won, and Nissan had to pay out $24 million. It all happened because high temperature. At high temperatures, it accelerates the parasitic reaction. What is a parasitic reaction? Well, it happens close to the anode side here. On what you see on the graph, on the slide here, close to the interface between electrolyte. I should have moved this thing here, but anyway. So you see, the red box here, that should be close to here. Oops, sorry. They should be between the interface of graphite and the electrolyte, and right at this border. So it is better explained here. There's a nice video on YouTube how lithium-ion batteries work from Learn Engineering, and you can watch it. You will see this is the graphite and this is the cathode. In between there's electrolyte. The right at the interface here, you start seeing gunk. That means unnecessary products that limit the diffusion of lithium to other side. So if this gunk product starts building up, so actually, it is a blessing in disguise. The very first cycle, there's a small buildup. That's good, because without that, the electrolyte will completely degrade continually, and you won't even get 100 cycles. So the solid electrolyte interface is a good thing, but only for a short time. And if it keeps building, then it's not good. Solid electrolyte interface has to be thin, and it has to remain structurally stable for thousands of cycles. If you start using at high temperatures, then on top of the SEI, you start seeing unnecessary products that will limit lithium. So what happens is lithium that is stuck in anode can't get out, and lithium that is on the other side can't get in. So slowly your Tesla Model S is losing capacity. Why? Because the parasitic reactions degrade the chemistry of electrolyte and byproducts build up here, and there's a thick wall that then the lithium has to penetrate this wall. So the range goes down from 270 miles to 240 miles because there is a thick layer of gunk that is unnecessary. And if you start using it in very high temperatures, then you accelerate this buildup. And in fact, Nissan Leaf, if you start using Nissan Leaf on a highway and if you start cruising at 70 miles an hour for 2 hours, then it actually shows an indicator, well, it's time to slow down. And you can't really fast charge after cruising at 70 miles for 2 hours. Leaf doesn't let you fast charge, DC fast charge, because the battery, the system, they know that, if you start fast charge, you just use it on the highway and then you start reversing the shuttle, it leads to unnecessary byproducts and chemical reactions.
This is just mind-boggling to me that I get it. I understand, early Nissan Leafs didn't have liquid cooling, but even their new ones, the Nissan Leaf Plus with the 200 plus miles of range, still does not have any liquid cooling to help manage the temperature of the batteries, and it just doesn't make any sense to me. I confirm this too with Nissan's PR. And they did say that they felt like they didn't need it in their batteries, in the battery pack. And the only thing that I can, boil it down to is the cost. In order to keep the costs low and profit margins reasonable, they opted not to add that in there. And it's amazing to me. So if you're watching this video and you're considering buying a Leaf, just understand that if you live in a place that is susceptible to extreme temperatures, hot or cold, or you need the car to perform really well. For example, if you're going up a huge mountain in Colorado, you're going to have some performance reduction.
That's right. And Nissan, for the biggest market is Scandinavian countries, Norway, Denmark, where the temperatures are really low, where they don't get into some of these high temperature issues. Maybe that's one of the reasons. As you said, profit margin and keep the cost low. That's definitely one of the big reasons. But it's still, I can't believe they don't do it.
Can you go back to the life cycle, the charge cycle graph? I've got a question about that. So I had a battery replacement almost a year ago now, and I was not an upstanding electric vehicle owner citizen. I was that blue line, I think it is, where I was charging to 100% on a daily basis. I would just plug it in when I would get home in the evening time, and the top end would be 100%, and so it would sit at 100% for probably hours, 3, 4, 5 hours before I would get up in the morning and drive it. It's remarkable that how much of an positive impact it has when you just reduce the top end charge to 80 or 90%. I will say now, since I got the new battery pack, I have been very, very good. I've taken care of the battery pack and set the top end charge to 90%. My question to you, Ravi, is why doesn't Tesla do a better job at educating owners on the negative impacts of charging to 100%? They just have a little message in there, but there's very little education around the true negative impacts of doing that. What are your thoughts on that?
Right. I think that's a disconnection between engineers on one end, the marketing team on the other end, and the sales and production team. So what the people know at R&D team, in the R&D team, doesn't carry over to the production, and then the marketing team does all the brochures and the material on the websites and all that stuff. Maybe because there is a disconnect there, if the engineers, for an engineering standpoint, it would make absolute sense to let your people know, customers know, hey, if you charge it only to 80%, you don't have to replace, or you will get better life out of your battery. And I think Tesla is actually one of the companies that does a little bit of that, not completely, but a little bit of that. There are companies that absolutely have no idea. These are car companies, GM, Actually they had a really good engineering team. So they had 18 kilowatt hour pack, only 14 was usable, 13 or 14 was usable. So there was a buffer of 5 kilowatt hour. And that's why I have seen many Chevy Volts perform really well with many very less degradation. But on a pure EV, you want to get as much energy range as possible. It goes back to that the conundrum, the slide I showed: cost, energy density, and cycle life. You want to maximize the cycle life. How do you do that? By limiting to 80%. But then your energy density is going down because you're only charging to 80%.
What are your thoughts on Audi's and Jaguar's approach of significantly limiting the access to the battery pack? So, the Audi has a 95 kilowatt hour battery pack, but I think it only has access to maybe 85 or somewhere around there.
Yeah, I know that could be a smart way to get longevity out of the pack. It is pretty easy for a battery engineer to just, hey, oh no, if I have 95 kilowatt hour, just use all 95. But that's not a wise thing to do. If they want to maintain their reputation of high quality, high performance, and long lasting vehicles, they have to have these kind of measures in place to make sure the batteries last at least 8 years, at least the warranty period they mention. It's a terrible thing to purchase a vehicle and then it's bad for the company to replace something, and it just adds to their overhead cost. So I think Audi is being smart about it, but how much they have limited, I don't know. But if they have done it, I think that's smart of them to do.
Yeah, I've always wondered if charging to 100% is truly bad, which it appears based on what you've shared, it is. Why does Tesla allow owners to charge to 100%? I understand that sometimes you're on a long road trip and you want to really maximize, the range, but if it's not good for the battery pack, why does Tesla allow it?
What we see as 100% usable, and there will always be some buffer. If you completely deplete the battery, you're actually causing some irreversible damage. So I'm pretty sure there is a buffer, but that buffer may not be as big as the Chevy Volt or the Audi e-tron or something, but I'm pretty sure there is a buffer. That buffer is, that protects all the cells. If you completely deplete the battery, I mean, from 4.2 to 3, completely deplete 2.6 or 2.8, then it'll cause some irreversible damage. So I'm pretty sure they, if it is a 95 kilowatt, 100 kilowatt hour pack, maybe they limit it to 97 or 95, but the exact number I don't know, but I'm sure there is a buffer. Is there any, I mean, I know I'm not a Tesla owner yet, so I wonder if you, as a Tesla owner, can you comment something on, have you seen any text in their manuals or anywhere they say, hey, you can set the charging upper limit to 90% and it's good for you? Have they mentioned anything like that?
They do. I don't know if it's in the actual manual, but they do recommend. I've seen from multiple sources, employees, that their recommended top end charge is 90%, and they only recommend 100% when you're on road trips. So, and I can confirm that there is a buffer there. I with my first battery pack, the 60 kilowatt hour battery pack, uh, as I said, I was not a very good EV citizen, because not only was I charging it to 100%, there were a few times that I ran the battery down, and it runs off of a reserve. You do have a small cushion there, which is why when you hit zero, you can still drive the vehicle. And the newer the battery pack, the more cushion there is. What I noticed over time is that that cushion got less and less, and the impetus for the replacement of the battery pack was that I was driving home. I had about 10 miles left to get to my house, and the battery actually shut down at about 32 miles of range that it indicated on the screen. And what Tesla determined, they ran a remote diagnostic and they determined that the battery was imbalanced. So that's actually a question that I have for you, what exactly that means, but I'll just finish the rest of the story. So they determined that the battery pack was imbalanced, and they ordered a new one, replaced it because they didn't make the 60 kilowatt hour battery packs anymore. Like a true 60 kilowatt hour battery pack, they replaced it with the 75, and that has been the magic, the golden ticket to me. The 75 has been enough, just enough for me to get around and do my driving for my real estate business, and come home every day with 20% left of range. So when a battery pack is imbalanced, what exactly does that mean? Can you shed any light on that?
Well, I guess some of the cells, when they go bad, so there's a very sophisticated battery management system. But what happens is one of the modules will have lower capacity than the other. Then over a period of time, it gets worse and worse, because then the running conditions put extra pressure on it's like you have a fractured leg and you're still trying to run the same race, then you're making the thing worse. So over a period of time, so that's why they they have 16 modules, right? That's good, because even if one fails, there are others 15 can take up the load of the one. But if as a couple of modules get, you said you were charging 100% all the time. So the couple of the cells in some of the modules may have gone bad, or they have lost there's something called impedance. The cell, just like every material has resistance, electrical resistance, cells have impedance. So this impedance buildup increases with the more parasitic reactions, and the buildup is not linear; it is exponential. So once it gets to a point where then it keeps progressively getting worse and worse. So one pack gets really bad very quickly after a point. Then the other modules have to take on the load. So that's my understanding of imbalancing, where some of the modules are in pretty good shape while the others are not. Sean, thank you. It's been a long discussion, but I hope it is a good one, and I want to thank you, because it's always good to connect with people who are passionate about the technology, and I've enjoyed your videos, and you gave me a platform to share some of my thoughts and experiences and discuss a few things with you.
Absolutely. And I can tell that there's a very, very bright future for you in a long career in this industry. You're very knowledgeable. You're very approachable as well, and easy to talk to. And as I shared in a previous phone discussion, I think it'll be a long-standing relationship. Of course, depending on who you end up working for, you may be able to share less information and less insight about some topics. But I just wish you lots and lots of success, and I know that will come. So a big thank you to you for your time commitment to prepare this presentation, and thank you for your time for jumping on this and just sharing your incredible insight into the industry. I think what I'll probably end up doing is breaking this up into some segments. I don't know what time we started, but I know it's definitely over an hour of our conversation. So I might break it up into several videos. That way it's easier for people to digest over a period of time. Is there any other lasting thoughts or comments that you'd like to share with those that are watching?
Well, I think we have covered most of the important topics. Maybe you can group some of the important topics into one video where it seems cohesive for people to follow. But I think we covered a lot of good topics, some details, technical details. And if some things are, not clear, I'm happy to share all the details in the links. So I can share it with Sean. You can make it public. And the more people get educated about it, it's better. They appreciate the technology. They get invested into it, and it is just a win-win for everybody. So I'm happy you're doing what you're doing, and it's all good. And thanks again. And I want to thank all the people who are interested and watched this interesting discussion as well.
Yeah, well, thank you everyone for watching so much. I appreciate everyone's time and attention. I know it's very, very valuable, and I never ever take that for granted. So thanks for your time. I appreciate everyone giving this video or videos a watch, and would love to hear your comments down below of what you thought about this. Maybe one thing that you learned that you didn't know before watching this. So we'll sign off there. Sean from All Things EV. See you all on the next video.